Somewhere in our solar system, rain falls and never touches the ground. It evaporates in midair over and over, as if the sky itself refuses to let it land. This world has been crying the same tears for roughly 300 years in an unbroken, punishing loop, and not a single drop has ever escaped its fate. So what keeps a planet like this alive, spinning in place, trapped in the rage of a sun that should have long since burned it into nothing? Picture rain that begins high in the clouds, falls for kilometers, and simply vanishes before it ever reaches solid ground. That planet is Venus, our closest neighbor by distance and, in almost every other way, the most alien place in the solar system. The reason nothing ever lands is written directly into the numbers. Venus's average surface temperature sits at about 464 degrees Celsius, 867 Fahrenheit, hot enough to melt lead, and that heat is more than enough to vaporize every drop of sulfuric acid rain long before it can complete its fall. Astronomers have a name for rain that behaves this way: virga, precipitation that visibly falls from a cloud but disappears into the air beneath it, never touching the surface at all. But is this a one-time event, or does it keep happening? A 2024 study from the University of Washington modeled exactly what happens next, and the answer is that it never really stops. The sulfuric acid clouds are locked into a continuous rain-evaporate cycle. Droplets fall, hit warmer air lower in the atmosphere, evaporate back into vapor, and drift upward again to reform in the clouds above. A closed loop researchers have started calling, almost affectionately, suicide rain. There's a strange middle step in that cycle too. NASA Goddard scientists found that the smallest droplets, those under a single millimeter, don't just evaporate quietly on their own. Instead, they tend to merge with other droplets on the way down, growing larger before they finally succumb to the heat and vanish, adding an extra layer of complexity to what looks, from a distance, like a simple falling rain. Is any of this something we would even recognize as rain? Not really, and that's exactly the point. Venus has built a closed, self-consuming weather system that repeats endlessly, asking nothing of the ground below and giving nothing back to it. Planet that cries but whose tears never once reach the Earth. If none of that rain ever lands, the next question follows naturally. Where does it keep coming from in the first place? To understand where Venus's rain originates, you have to look up, way up, into an atmosphere so thick it barely resembles a sky at all. The planet's sulfuric acid clouds don't form a thin, wispy layer the way clouds do on Earth. They build into a genuine barrier between the surface and space. Just how big is that barrier? NASA and the European Space Agency have mapped it out. The sulfuric acid cloud deck spans 20 to 30 kilometers in thickness, sitting at an altitude of 45 to 70 kilometers above the surface, packed with droplets so concentrated they range from 75% to 98% pure acid. This isn't rain in any ordinary sense. It's a dense, corrosive fog layer stacked kilometers deep. And the punishment doesn't stop at the clouds. Beneath all of that, the atmospheric pressure at Venus's surface is 92 times what we feel at sea level on Earth, equivalent to the crushing pressure found 914 meters deep in Earth's oceans. Anything sent down through that cloud deck isn't just facing heat. It's facing a weight that would flatten most machinery built for space. Here's where it gets genuinely strange, though. At the very top of those clouds, the temperature drops to around degree 5, colder than winter freeze on Earth. Directly below sits at a blistering 464 degrees Celsius. That's a swing of more than 500 degrees Celsius packed into a vertical distance of only about 60 kilometers, one of the sharpest temperature gradients found on any rocky planet in the solar system. Is there anywhere else in our solar system with a contrast this extreme top to bottom in such a short span? Not among the rocky worlds. Venus holds that record outright. One planet, one atmosphere, and two completely different extremes of survival stacked directly on top of each other. With an atmosphere shaped like this, the next mystery isn't the clouds themselves, it's what's making them move. The first thing that should strike you about Venus's winds is how impossibly fast they move compared to the planet carrying them. At the upper cloud layer, winds tear across the sky at 360 km/h, 224 miles per hour, fast enough to circle the entire planet in a fraction of the time it takes the planet itself to complete a single rotation. Scientists call this phenomenon superrotation, and it means the atmosphere spins up to 60 times faster than the solid ground beneath it. How is that even possible? The clouds of Venus complete a full circuit around the planet in just 4 Earth days, while on the planet's Saturn rotations added 43 Earth days to finish. It's one of the strangest disconnects in planetary science. An atmosphere essentially racing around a planet that is, by comparison, standing almost still, and researchers still haven't nailed down the exact mechanism that keeps this superrotation going. The storms riding on top of that wind system are just as strange. In 2006, ESA's Venus Express spacecraft discovered a massive S-shaped atmospheric vortex sitting over the planet's south pole, roughly 2,000 kilometers wide, a swirling storm system that behaves less like a passing weather event and more like a permanent self-sustaining fixture of the planet's atmosphere. And the winds aren't even stable at their current speed. A 2024 study using data from JAXA's Akatsuki spacecraft found that wind speeds at Venus's equator climbed noticeably from around 300 km up to 500 km/h. Over the span of just a few years, a shift in the planet's climate that scientists still can't fully explain. Where does all of that raw energy come from? Wind and clouds don't generate themselves out of nothing, and on Venus, the source traces back to thousands of openings in the ground itself. Start with a simple fact. On Venus, volcanoes aren't just geological features, they function as an ongoing acid factory, constantly feeding the very clouds that make the planet so hostile. Just how many volcanoes are we talking about? NASA has catalogued more than 100 major volcanoes on Venus, along with at least 167 large volcanic landforms wider than 100 kilometers across, more volcanic structures than any other rocky planet in the solar system carries. Scientists estimate that roughly 85% of the entire surface originated from basaltic lava flows, meaning the planet's crust is, in a very real sense, built almost entirely from its own eruptions. Is any of it still active? A 2023 study published in Science found compelling evidence that it might be. Using radar data from NASA's Magellan spacecraft captured back in 1990, researchers noticed that a volcanic vent had visibly changed shape over the course of roughly 8 months. A strong hint that Venus isn't a geologically dead world at all, but one still reshaping itself in real time. That fits with how young parts of the surface actually look. Magellan mapped 98% of Venus's surface using radar between 1990 and 1994, identifying more than 1,000 impact craters and terrain in some regions estimated to be only 500 million years old. Remarkably young compared to the ancient, heavily cratered surfaces found on many other planetary bodies. And the scale of what these eruptions can release into the atmosphere is staggering by comparison to anything on Earth. The US Geological Survey estimates that volcanic eruptions on Earth release roughly 10 to 20 million tons of sulfur dioxide per year. On Venus, individual large-scale eruptions throughout its history may have injected hundreds of millions of tons of sulfur dioxide into the atmosphere in comparable timeframes, more than enough to build and continuously replenish the dense acid cloud layers we see today. The ground on Venus isn't just old rock sitting quietly under a hostile sky. It's still active, still venting, still screaming through its own cracks. And a planet with this much churn beneath its surface raises an uncomfortable question. Could anything actually be living in what it produces? Could a place this hostile, crushing pressure, scorching heat, clouds of concentrated acid, actually harbor life? It sounds absurd on its face, and yet this exact question has occupied serious scientists for years. It started in 2020, when researchers detected phosphine pH3 in Venus's atmosphere, a compound that, on Earth, is strongly associated with biological processes. The announcement ignited a genuine firestorm of scientific debate over whether microbial life might exist somewhere inside those acid clouds. That debate has a name and a face: the 2020 phosphine controversy. A team led by Jane Greaves at Cardiff University announced they'd detected phosphine in Venus's clouds using the James Clerk Maxwell telescope. The claim was picked apart almost immediately by other research groups within the same year, who raised serious questions about signal processing and possible measurement error. The result remains unconfirmed to this day, but the controversy at speaks one of the most talked about scientific disputes of the decade, and it directly helped push NASA towards selecting Venus as the target for 2 new missions, Da Vinci, US, and Veritas. So where exactly could life theoretically survive up there? Researchers at MIT and Cardiff University proposed that microbial life could potentially exist inside the concentrated sulfuric acid droplets in Venus's cloud layer, where acid concentration reaches as high as 98%, but where water can still exist in complex chemical combination with the acid itself. Their models even pointed to a specific size range. Those acid droplets measure roughly 1 to 3 micrometers across, startlingly close to the size of ordinary bacteria here on Earth. Is there any precedent for this on our own planet? There is. Research from Harvard and Caltech in 2021 confirmed that acid-loving microorganisms, acidophiles including certain species of archaea, can survive on Earth in environments as extreme as pH 0, conditions that overlap meaningfully with the acidic environment inside Venus's clouds. It's not proof of life on Venus, but it closes the gap between theoretically possible and biologically plausible. Taken together, the acid rain that makes Venus so lethal to us might, paradoxically, be exactly what shelters something else. Not a destroyer of life, but potentially its last refuge on a planet that has destroyed almost everything else. If life could have found a way to survive there, it raises an even bigger question. Was there ever a time when survival on Venus didn't require hiding in the clouds at all? It's hard to imagine now, but there's a real scientific case that Venus once looked a lot more like Earth than the inferno we see today. A 2023 climate simulation from the Georgia Institute of Technology modeled what Venus might have looked like if it held surface water early in its history, roughly 2 to 3 billion years ago. The result, a planet with a shallow ocean and thick cloud cover, a genuinely habitable-looking world, at least on paper, before something pushed it past the point of no return. That something was a runaway greenhouse effect, and it's one of the starkest cautionary tales in planetary science. As temperatures rose, surface water evaporated into the atmosphere. Water vapor itself is a potent greenhouse gas, which trapped even more heat, which evaporated more water, in an accelerating feedback loop that didn't stop until the oceans were gone entirely and the planet had locked itself into its current furnace state. For a long time, that history wasn't obvious, and Venus's cloud-top conditions actually fueled the opposite assumption. At the cloud layer, pressure sits close to 1 atmosphere and temperatures range from 20 to 40 degrees Celsius, closer to Earth's surface conditions than anywhere else in the solar system. That resemblance is exactly why scientists once nicknamed Venus Earth's sister planet, long before missions revealed just how hostile the actual surface had become. That romantic idea left its mark on popular culture too. Carl Sagan, in his 1980 book Cosmos, famously described Venus as a world of eternal acid rain under pressure like the crushing depths of an ocean. Vivid language that helped cement public fascination with the planet for an entire generation, long before spacecraft data caught up with the poetry. A shallow ocean, a familiar-looking pressure at cloud height, a sister planet nickname, all of it makes Venus's transformation feel less like an alien anomaly and more like a warning written into another world's history. But everything we know about that history came from machines brave enough to go somewhere humans never could. How do we actually know any of this about a place this violently hostile? Not from telescopes alone, from spacecraft that flew straight into the furnace, fully aware they wouldn't survive it for long. The clearest example is the Soviet Venera 13 lander, which touched down on Venus's surface in 1982 and kept transmitting for 127 minutes at 464 degrees Celsius and 92 atmospheres of pressure before it was finally destroyed. In that short window, it sent back the first color photographs ever taken of the planet's surface. Glowing orange, alien, and utterly unlike anything humans had photographed before. It remains one of the greatest achievements in the history of space exploration, and it opened the door to everything we now understand about this brutal sister planet. Venera 13 wasn't the first to try, though. Venera 9, launched by the Soviet Union in 1975, was the very first spacecraft from Earth to land on another planet and successfully transmit images back. But it only survived 53 minutes before the heat and pressure crushed it completely. Why did Venera 13's images come back glowing orange rather than the blue-white of daylight photos on Earth? Analysis of that data confirmed the answer. Venus's dense atmosphere filters out nearly all blue light before it reaches the ground, leaving the entire surface bathed in a persistent orange glow, even during what would count as daytime. Building machines that can survive conditions like that even briefly is its own kind of engineering marvel. NASA has since developed a specialized acid sensor for its upcoming Davinclis mission, built from acid-resistant materials like quartz and synthetic sapphire, engineered to withstand 98% sulfuric acid concentration and temperatures of 475 degrees Celsius for a full 60 minutes. A genuine feat of materials science built specifically to explore what people have started calling the crying planet. Humans can't set foot on Venus. Not now, maybe not ever, but we keep sending machines to die there anyway, one mission at a time, purely because we want to know. And once you understand how extreme Venus is, the natural next question is whether anything else out there could possibly be worse. Venus already sounds like the worst place imaginable, but is it actually the most extreme weather in the universe we know of? Not even close. Consider HD 19733b, a gas giant exoplanet located 64.5 light-years from Earth, discovered by the Hubble Space Telescope in 2007. It doesn't rain acid, it rains glass. Molten silicate particles sweep sideways across its atmosphere at roughly 5,400 kilometers per hour, driven by winds so extreme that rain barely describes what's actually happening there. Venus has its own reality-bending quirk, though, one that doesn't require leaving the solar system at all. A year on Venus lasts 225 Earth days, while a single day, one full rotation on its axis, takes 53 Earth days to complete. That makes Venus the only planet in the solar system where a single day is longer than its entire year. The rotation itself is backward too. Venus spins in the opposite direction from Earth, and because that single rotation takes 243 Earth days, longer than its 225-day year, the Sun actually rises in the west there, with each full day-night cycle stretching out to nearly 3 Earth months. Is Venus's volcanism unique in the solar system, or does the same kind of process show up elsewhere? Not quite the same, but there's a useful comparison. Jupiter's moon Io experiences intense tidal heating from its gravitational tug-of-war with Jupiter, fueling the most powerful volcanic eruptions anywhere in the solar system. Venus's volcanism works differently, driven by internal heat rather than tidal forces, but the result rhymes. A continuous supply of fresh material, in Venus's case sulfuric acid particles, being pumped endlessly into the atmosphere above. There's apparently no upper limit on how strange planetary weather can get once you start looking beyond our own solar system. And even with everything we've covered about Venus itself, the honest truth is that what we don't know still outweighs what we do. We've covered a lot of ground on Venus already, so what's left that still leaves scientists genuinely stumped? Start with something unexpected. ESA's Venus Express mission, active from 2006 to 2014, detected a thin ozone layer at an altitude of 100 kilometers in Venus's atmosphere, structurally similar to the ozone layer that protects life on Earth. Finding it on a planet with no known life by our current understanding was a genuine surprise. That ozone layer came with its own unsolved riddle. In 2011, researchers identified what's been called an ozone hole in that thin layer, one that can't be fully explained through ordinary photochemistry, the standard set of light-driven chemical reactions scientists use to model planetary atmospheres. It suggests Venus's atmospheric chemistry runs through cycles far more complex than current models can fully capture. If life really is hiding in those clouds, how would it even survive the planet's brutal vertical extremes? MIT researchers built computer models in 2021 suggesting that any hypothetical organisms would need the ability to essentially hibernate as they sink into the lower, more hostile cloud layers, then wake up again once wind currents carry them back toward more hospitable altitudes. An extreme almost science fiction survival strategy for an extreme almost science fiction environment. And the phosphine question still hasn't gone away. In 2020, an international team led by Jane Greaves detected phosphine at a concentration of 20 parts per billion in Venus's atmosphere. Even though the finding remains contested, that single controversial measurement has driven a wave of new research into the possibility of life on the planet, research that's still actively unfolding today. The deeper scientists dig into Venus, the more it seems to hide rather than reveal. Fortunately, the next wave of missions is built specifically to close some of these gaps. What's actually waiting on the horizon for this crying, screaming planet? As it turns out, quite a lot. Venus is about to become one of the most heavily studied worlds in the solar system all over again. Leading the charge is NASA's Da Vinci Plus mission, targeted for launch in 2029. It'll be the first mission to descend to Venus's surface since the Venera landers, carrying a mass spectrometer designed to analyze atmospheric composition and precise measurement of pressure, temperature, and noble gas isotopes, all in the hunt for any lingering trace of ancient biological activity. Right alongside it is NASA's Veritas mission, targeted for launch before 2030, which will map Venus's surface by radar at a resolution of 30 meters, a dramatic leap over Magellan's 100-meter resolution from the 1990s. The goal is to spot signs of ongoing geological activity and finally settle the long-standing question of whether Venus once had oceans of its own. ESA is bringing its own contribution to the table as well. Envision, targeted for launch in 2031, will use radar to map Venus's surface at unprecedented resolution, searching specifically for signs of active volcanism and precisely measuring surface temperature to help reconstruct the planet's full climate history. To put the sheer scale of what these missions are studying into perspective, a 2023 study from Arizona State University estimated that if every drop of sulfuric acid in Venus's cloud layer were somehow collected and poured across the entire planet, it would form an acid ocean roughly 10 centimeters deep, covering every square kilometer of the surface, a striking illustration of just how much material is constantly cycling through that atmosphere. The tears of this planet are, quite literally, about to be reached by human machinery for the first time in decades. But Venus's story isn't really just about a distant alien world. It might be a story about where we're headed to. Go back to where we started. Rain that falls and never once touches the ground, evaporating endlessly in a loop with no escape. That image of Venus, a planet crying without ever shedding a single tear that lands, turns out to be more than just a striking picture. It might be a warning. Acid rain isn't unique to Venus after all. On Earth, acid rain with a pH below 5.6 causes an estimated $50 billion in damage every year to buildings, infrastructure, and ecosystems across North America alone, according to environmental agency estimates. The scale reaches even further than that. According to United Nations Environment Programme reporting, acid rain across regions of China and India has damaged numerous World Cultural Heritage sites. And at various points throughout the year, an estimated 6 billion people worldwide live in areas where acid rain levels exceed recognized safety thresholds. So here's the uncomfortable question worth sitting with. Is Venus simply an alien curiosity, or is it a preview of where a runaway greenhouse effect could eventually take a planet like ours if it's ever pushed past its own point of no return? The planet that cries forever isn't just a story about a distant, hostile world spinning alone in the dark. It might be closer to home and closer to now than any of us would like to think.